Хочу. Ты сказали, что он зовут зовут?
Я сегодня в шорте и в маечке. И как побежал обратно. Холодная какая.
Мы вышли в солнышко. С беспокойством направо. Там,
Направо,
где туча. И мы спросили, Сережа, ты взял солнышко? Я думаю, что это шутка. Солнышко, какой зонтик. Мы не дошли к столу.
И поэтому, в частности, может быть, юрист, на религии мы не будем рисовать. Там возникает наша решение. А дальше, как мы рассматриваем, сигма квадрате, как раз замкнем, один будет еще. А если рассматривать тогда же у нас тоже
Ага, сейчас пошел. Я не взял свои защитные механизмы, надо ехать. Но я думаю, он не будет целый день.
я согласно прогнозу, целый день. Согласно прогнозу,
Да.
So, we are pleased today to begin with the second talk of Garoufalidis, who will speak about asymptotics.
Thank you. Sorry for the change, of title. I thought of finishing the story of last time rather than get into a different story about coefficients of the Jones polynomial and their relation to graph countings. It's an interesting story. It has to do. That story was joined with Sergei Norin, who's mentioned in a previous talk. But I thought that I should maybe tell you a little bit more about the structure of quantum invariants and not get into the graph counting. So graph counting would be one way to, in fact, categorify the coefficients of the Jones polynomial. But what I want to tell you today is a different idea and perhaps an answer to the question, how do you categorify an analytic function? Okay? I will tell you what kinds of analytic functions I have in mind, of course, concretely. So let me kind of begin a little bit by historically, about 3 years ago, I want to tell you a few things about Qseries, which are, that is Q hypergeometric series. So 3 years ago, at the end of the conference in Diableret, Don Zakir and I were in the train to Bonn, and I had looked at the following knot. Now, this is of course not a knot, this is a planar graph. It is actually a planar trivalent knotted graph. Now, you may argue that this is not very knotted, but I want to take that one, okay? And it has a Jones polynomial, and it even has a colored Jones polynomial colored by n. So the colored Jones polynomial of this object is a Laurent polynomial in one variable.
I'm sorry, why do you write n at each edge?
Because every edge, it's a spin network, and a quantum spin network, and every edge has spin n.
You are one and too much.
Huh?
Spin.
Too much? Oh, yeah, right. Oh, sorry, that was the question. Okay, so you get a sequence of polynomials, one for every n, and in fact what turns out is that if you take this sequence of Laurent polynomials and you shift it all to the right, the constant term is always 1. And what happens to these coefficients is that they actually stabilize. Namely, if you shift first, and then you look at the coefficient of q to the 10, when n is greater than 10, that integer is the same independent of n. And therefore, the coefficients stabilize, and they stabilize to an infinite series, and that infinite series is g of q, which is nothing but q infinity times sum from 0 to infinity of minus 1 to the n q to the n 3n plus 1 over 2 over qn cubed, where qn is the usual and q infinity is, as you can tell, which is a well-defined formal power series. So where is this? This is a formal power series with positive powers of q, non-negative powers and integer coefficients. It's very important that they're integer coefficients. And in fact, concretely, it's 1 minus q minus 2q squared minus 2q cubed minus 2q to the 4 plus q to the 6. Based on this, what would the conjecture be? Of course, you can expand more, but I'm not going to expand to 50 digits, and so on. But what perhaps you may think that this series actually has coefficients which are bounded between minus 2 and 2. If that was the case, it would have nice modular properties. It is not the case, actually. If you go further down, you will see that the coefficients exponentially grow. And in fact, this series has no modular properties that we know of. So, empirically, that means numerically and non-rigorously, Don Zahir and I found the following thing. So, one thing is clear. This is, first of all, a formal power series with integer coefficients. Second of all, it is an analytic function. So when q is e to the 2 pi I z, and q is less than 1, so inside the unit disk, in other words, z is in the upper half plane.
I'm sorry, if q is an exponent, then the epsilon's value is exactly 1. The z is converted. Okay, good.
Upper half plane.
Yes.
Yes, so in the upper half plane it converges, or inside the unit disk, if you like, it converges. And it converges because basically this is quadratic, in epsilon, and this is only linear in epsilon. You can check it, So if it converges, then you can evaluate it wherever you want inside the unit disk and get a well-defined complex number. That's not what normally comes to mind, but anyway, empirically we found the following. So if you have a series which converges inside the unit disk, and you want to study modular properties or whatnot, the thing to do is actually go to the limit, right? Just go to the edge, and then see what happens. So when you go to the edge, we found the following, that empirically, that g of e to the 2 pi I z as z goes to 0 has an asymptotic expansion of the form root z times a of z plus root of minus z times a of minus z, where, not this one, where a of z,
So can we see the last one? Yeah.
last one?
Yeah, so you
Write it once
you
again.
wrote the formula. and-
Oh yeah, that was not very smart. Root z times a of z and root minus z times a minus z. Maybe I will just put it here. I want to keep the picture though. Where a of z is z to the minus 3/2 times a power series a and z to the n from 0 to infinity Okay, and these coefficients are some numbers as usual, but take some time to recognize. And the first few of them are like that. And this a of z, so empirically we found this, where this is true, and in fact a of z are the asymptotics of the Cauchy invariant of the figure 8 at q equal 1. Okay, remember I told you that the volume conjecture, the generalized volume conjecture for figure 8 is an expansion like that for some power series which live in the invariant in the trace field. The trace field is square root of minus 3, and there are powers of I that are absorbed here. So we found that somehow this quantum spin network, this very basic one, has something to do with the figure 8 via this series. In fact, the reason, the way we recognize that this series was indeed related to the figure 8, believe it or not, had to do with this number 697, which both Don and I had computed. So when we first computed the asymptotic expansion here to third order, we both recognized the numerator 697. We said, I've seen that one. And Don actually grabbed his files and he figured it out that this is figure 8. And then from then on we knew what we were doing. And empirically we found out. Now we have a proof, by the way. There is a theorem of Don Zagier and Gamma, I guess. In the last 2 weeks, we found the proof of this statement. But the mystery remains, which is what does this tetrahedron have to do with figure 8? And it has something to do via this Q series. So I promised, so this was kind of a mystery to us, but there is more mysteries. So okay, I told you about this theorem, that this is now rigorous, but I will tell you another one, which is even more fun. So here is the other theorem that also was a conjecture, but now we can prove, and says the following. So consider a new series in X, which is e to the c times a of 2x over 1 plus x, a of minus 2x over 1 minus x, minus e to the minus c times a of 2x over 1 minus x times a of minus 2x over 1 plus x. And this is a formal power series with actually complex coefficients. In fact, real coefficients, because C is a real number. Okay? For instance, what is the constant term? You just put A equals 0, A of 0 is 1, so it's e to the C minus e to the minus C. That's a number. What kind of number? Real number. Not algebraic number. Well, it's not known, because actually it is not known whether e to the C is irrational. As I said, if you can prove that e to the C is irrational, that's probably a Fields medal, a hard problem in transcendence theory of periods. These are periods of weight 2. These are values of the dilogarithm of certain algebraic integers. If you could prove that the exponentials of values of dilogarithm of algebraic integers were, transcendental, I mean, that would be a great result. It would have applications to motive cohomology and would probably follow from motive cohomology, but you just can't prove that, just can't. All right, so this series A, and there is a precise formula to all orders. I only gave you the first few coefficients, but there is a closed formula in terms of a formal Gaussian integral, but I'm not going to write that formula down. But believe me, that series A of X is factorially divergent. Meaning what? Meaning the nth term grows like n factorial. So if I have a factorially divergent series and another factorially divergent series, what do I get? Typically factorially divergent. Unluckily, if I take a factorially divergent series that starts with 1 and I multiply it with 1 over it, which also starts with 1, I get 1 which is very convergent. But that rarely happens, right? This one is not the inverse of that. So this series is factorially divergent, this is factorially divergent, the product of them is factorially divergent. Well, how factorially divergent? Why don't I just give you a little bit of data here? The coefficient of a to the x in this series, the 20th coefficient is 2.69 times 10 to the 20, and the coefficient, the 100th coefficient, after that we start losing precision, is 3.13 times 10 to the 174. That's how fast these coefficients grow. Now I'll give you the same data for the coefficient of q to the x. I mean, these are exact, numbers, kind of. 20, I think. It's minus 0.009177, and the coefficient of x to the 100, it's even more fun, it's minus 0.093922 and keeps going. So what do you see? Something collapses. The exponential growth actually collapses, and in fact the theorem is, if you consider that, I'm sorry for inserting definitions into the theorem, then Q is analytic. That means convergent power series for x less than 1. Okay? That's kind of fun. We proved it. First, we checked it numerically, much to our disbelief. Stuff like that is not supposed to happen. They're not supposed to kind of resound like that. So, okay.
Sorry, quick question. So C is the volume of the formula?
Yes, over 2 pi. Okay, so what does that have to do with the figure 8? And why are we getting... the picture that I want you to remember is the following. This theorem here, which was empirical but now shown, says the following. If you take this Qseries and you look at it at radial limits, it has the same asymptotics as the radial limits of the Qseries invariant, which is only defined on the unit circle. So the Qseries invariant is only defined on the unit circle. The series here, G, is only defined inside, and the radial asymptotic match. And they match not just at q equal 1, but as we all know in quantum topology, they match at every root of unity, where you have to replace this A by the corresponding A at the root of unity, and that's still a theorem. That theorem we prove with Donzagier, we have it at all roots of unity. So okay, something goes radially, something goes, you know, along the circle, and they match. But this is really an invariant of a knot. This is the Qseries invariant of a knot. This little series G, this particular Q series, you may say, why is it a knot invariant? I only know it for the figure 8, and I don't even know it for the figure 8. All I know is a formula. So what does that have to do with figure 8? That was the mystery. And also, why do you actually get convergence as we have? So that's mystery. So, but I'm going to tell you about the resolution to this mystery that we found recently, meaning in the last month, in fact. And this is not written work, but has not been written, but some parts of it are written, so I can tell you. So there, to explain the mystery, there are actually 3 kinds of invariants of manifolds with torus boundary. These are invariants of manifolds with M, with torus boundary, like knot complements. One are state sums, like Reshetik derived, like Qseries, the ones I told you about, I gave you many formulas. Another is state integrals, and another is Qseries. So I told you a lot about state sums. I want to tell you a little bit about state integrals. They are much more recent invariants. So let me tell you about state integral invariants of knots. Knots. To begin with, they are not numerical, they take values in analytic functions. First of all, they were constructed recently by 2 groups, Andersen and Qseries, in 2 papers, in fact, and also Qseries, Luo, Bannoe. Okay, so they exist. They are topological invariant. The input, it's good to know what is the input. The input is a knot. Well, not really. The input is an ideal triangulation. Much like the ones we have heard already about, the ones we know and love. Basically, the dual to a standard spine.
These invariants of hyperbolicals.
They are topological triangulation, so you can do them even for the trefoil. Although I can.
What do you mean by an ideal triangulation? That's a hyperbolic term.
All vertices are on the knot.
All vertices are on the knot. Don't worry.
I see.
And the output, so at least let me tell you what is the output. The output is a holomorphic function Im of B, which is defined on the cut complex plane. So this is the complex plane where I cut it at the negative axis, real axis, including 0. Okay, that's input, that's output. And they have a built-in block. So the building block, which is the analog of the quantum n factorial, so the building block is Faddeev's quantum dialog. I'm not going to define it. It's a special function, but highly transcendental with meromorphic properties and wonderful identities. But that does not satisfy any differential equation, nonetheless. And I want to give you some examples, so concrete examples. So you know, what is phi b? It's an analytic function. If you actually see, you will not quite appreciate it. I mean, maybe I can just say it doesn't really hurt, although it causes more confusion than 4 sine h of WB sine h of W over B times W. Well, you know, that's whatever. That's what it is. And I will give you examples. So the invariant of the figure 8 is a single integral over R, slightly moved above, of phi b square of x e to the minus pi I x squared dx. And the value for the phi 2 is the same, except we replace 2 by 3. And I'm not going to repeat the joke. If I ask you the value for the 6-3 knot, I'm not going to replace 3 by 4. It's going to be a W. Okay, that's kind of a typical example. I take this special function, which you really don't want to think too much about, and I do an improper integral, which actually is convergent. I mean, at infinity, and gives me an analytic function. Okay? So these are invariants that exist. I mean, topological invariants, new topological invariants of knots. And I want to pose a question here. I just think about it. You know, how to categorify these analytic invariants. Okay, I actually have an answer. Okay. But for now, you may wonder, you know, of course, analytic functions are great, especially if you want to study asymptotics, right? Because the Qseries invariant or Asymptotic derive is a sequence of numbers. If you have a function, you can study asymptotics by moving contours of integration and whatnot. Okay, good. So that was my second egg of the 3, and the third egg is called Qseries. Because I already gave you an example of a Qseries, but I want to tell you Qseries invariants of knots, honest invariants of knots, just like those were honest invariants of analytic invariants of knots. Okay, so Qseries invariants of knots. So another recent story. First of all, they were introduced in a series of papers by physicists, 3 brave physicists, Dimofte, Gayotto, and Bukov, on something called the 3D index of some quantum field theory. Okay, they were introduced by that. Necessary and sufficient conditions for convergence were given by me, and topological invariance, but only for hyperbolic knots. Okay? For the other knots, they are not even defined because they fail these conditions, are given by a paper of Greg Hodgson, basically Australia plus me. Hodgson, Rubinstein, Segerman. This guy is British but lives in Australia. Okay, or live in Australia. So they were introduced by this. The input is an ideal triangulation, but as I said, not every ideal triangulation is good. Namely, not every ideal triangulation makes these Qseries I'm going to write down convergent. It's only those that are good that matter, and goodness is something that physicists don't care because they can compute and don't care about non-goodness. But goodness is an important property, so I'll tell you what is a good ideal triangulation because it has a very nice, sexy definition. Good means one efficient. Okay, back to the 1960s normal surfaces. It means that there are no normal surfaces which are topological spheres or tori. That's why you're forced to only take hyperbolic nodes, like not a connector node. Okay, that's input. Output, there are two kinds of ways to talk about output. I mean, I'm going to talk about manifolds with three boundary. One boundary component. So it is for every pair of integers, you get a formal power series in the variable q to the 1/2. So it has integer coefficients, but it may have negative, find me many negative powers of q. Find me negative and I many positive. So this is I m of m e of q, right? And m and e is a pair of integers attached to the node complement. M is not the meridian, and E is certainly not the longitude. What is M and E? Every physicist knows that M is magnetic and E is electric. So since this is a conference in Magnitogorsk, I thought that was a funny thing. Okay? All right, now you can actually sum the series up. I mean, you can take a sum. So rather than having one Q series for every pair of integers, you can actually sum them appropriately, and let me call it total. So total is just a single series once and for all, for every node complement. So this is who introduced it, this is input, this is output. I have to tell you about building blocks, so maybe I put here building blocks.
So to get the total, do you take some sum over L?
Yes. Yeah, I'm going to take a sum over E, yeah. So these are sums over lattices.
Without multiplying by powers of an auxiliary variable.
Yeah, to make them convergent, right? I don't worry about that. I mean, so there is a building block. Before building block was spaghetti dialog, so I'm going to give you the building block here, which is the index of the tetrahedron, which is a specific and once and for all power series minus 1 to the n, q to the 1/2 n plus 1, minus n plus half e times m divided by qn plus c, and I'm summing over the integers. However, if n is negative, this is 0. So the sum is necessarily overcome. That's a building block. And let me give you an example, and I'm only going to do the figure 8. And the example of the total index for the figure 8 is the sum where k1 and k2 are integers of I delta k1 k2 times I delta k2 k1. Okay? I'm summing over pairs of integers. This is a well-defined power series, so that this converges as long as what I'm summing, sufficiently grows. Right? So, for instance, this one does not really make sense. This I cannot sum, but does not converge in the whatever I add to the topology. Okay, so this is the example for the figure 8. Alright, so now I can tell you about the combination theorem. So I told you about the 3x state sum, state integrals, and Qseries. These Qseries are not invariants. So now I can come to the main point, and the main point is that there is a beautiful connection between state sums, state integrals and Qseries. so theorem. This has appeared and cleared through referee. So it has many parts. So the first part is together with Qseries. So suppose we take the total. Suppose we take the state integral of the figure 8, which I remind you was the integral of phi b square e to the minus pi ix, right, over R, this analytic function. This analytic function, I can write it as, I'm going to ignore some factors which are stupid. I mean, I don't care.
Why don't you write capital C instead of that?
All right. Rinat is not here, but still, the thing is, the more information you give, the worse it becomes. B, G, G? Where Q is e to the 2 pi I b, Q tilde is e to the 2 pi I over b. And little g is equal to sum minus 1 to the n times q to the 1/2 n plus 1 over this. And the big G is well, pretty much the same, although you probably will not have guessed that this is the formula. Q to the s n plus 1 over 1 minus q to the s. These formulas do talk to you if you actually are willing to listen. Okay, this is kind of the same as this, but it's being kind of messed up by an extra summation. Okay, this is one series and that's another series. Okay, now if you pay close attention to the blackboard, you will see that I have made something forbidden, namely I used the same letter little g for two different Qseries. Do you see that, Kent?
No.
You don't?
Yes, we
Okay. Is it really different? Yeah, sure. The denominator is a square, and the numerator is also something different. Right? Objection. Yeah, well, so first of all, since this is a not invariant, so is big G and little g. Right? Because this analytic function determines the big G and the little g. So this is a not invariant. Part B, together with Zagir, G equals G. Okay? This one is equal to that one. If you don't believe me, the first thing to do is go to the computer. Just grab your Mathematica and compute the first 100 coefficients here and here. They are integer numbers. Just do that. Do they agree or do they not? If they agree, they are equal. These two Qseries are equal. There are people who are specialists in Qseries identities. Actually, if you know a little bit of the trade, you can actually prove that you know how to do that. So in particular, these which are invariants of the figure 8, so the index, the state integral, all the information the state integral is packaged into two Qseries which are not invariants. Those two Qseries, one of them is this one, which is actually equal to that one, and the other one is the other one. And this is, in physics, is called the holomorphic block factorization. Whatever. Okay, so now, since the state integral is invariant not, that series is invariant not, and that invariant not is invariant the figure 8. So it's not a surprise that the radial limits of this little g that we empirically found were actually related to the figure 8. Now let me tell you the relation of the index. What about the total index? The total index of 4, 1, which I gave you a formula, that was the sum of the tetrahedron index of K1, K2 times K2, K1, right? So what's the relation between this and little g and big G? Notice that it's just the Q and not the Q tilde, so the answer is just the product of the two. So the index that we constructed is related to the state integral invariant that way. Okay, part C. Part D, so now I can remove a little bit. I don't know what to remove though. Okay, I'm going to remove the series. Okay, fine. I'm going to remove this series. Part D, and this is joined with Khashaev. So, you know, this is an analytic function, right? In the cut plane, in the left cut plane. I want a number. How do I get a number out of an analytic function?
By integrating.
No, by evaluating the function. If I have a function and I want a number, I just evaluate the function somewhere. Where? Somewhere where? At 0. 0 is not allowed. What is next choice?
1.
1. Thank you very much. That's exactly what we did. So that's the answer. Do you remember this number? That was the number that appeared in Theorem with Dom, the gear. And in fact, but that's something we have not proven. What we have not proven, but it's just a matter of writing it up. The asymptotic, the Taylor series of this analytic function at b equal 1 is the convergent series Q that I told you before. Okay, it exactly explains why that power series Q converged, and the radius of convergence is 1, because that has a singularity at 0, so the radius of convergence is 1. Okay, that is something that we have not shown, but it is sort of technical. Okay, so in particular, these functions can be evaluated, but this time, the values of these functions, because the functions themselves are transcendental, the values are sort of transcendental numbers, which are not invariants. So, and finally, in the days that actually Rinat was here, we evaluated it not at 1, but at 1 over n. You see, we cannot use negatives. Negatives are forbidden. Negative numbers are forbidden. 1 is okay, and remember that Q is e to the 2 pi I b. Actually, b squared. Oh, whatever. Let me not worry about that. So b equal 1 is the classical limit, because e to the 2 pi I is 1. And b equals 1 over n is the kind of nth roots of unity. So we can evaluate it here. And in fact, we evaluated and we found that it is a sum of two terms. So it's a sum of two terms. And each term is a not invariant. And that not invariant actually is the Baziak-Benedetti invariant of the figure 8 at that root of unity using the geometric representation of the figure 8. And we did that also for 5-2, and we did that for -237. But we haven't, that's last night, okay? Okay, so finally, in the last whatever few minutes, I can answer the question. How do you categorify state integrals? That is a state integral. It's an analytic function. How do you categorify it? Well, this analytic function is equal to the to a finite sum of products of Qseries. Qseries are analytic functions. The problem, I mean, this identity looks kind of trivial, but you have to keep in mind that each one of these Qseries is convergent only either on the upper or on the lower half plane. But this particular combination analytically continues to both right and upper and lower and on the positive axis. It glues together. So that's what this amazing state integral using the quantum dialog does. So if I wanted to categorify the state integral, I break it into a finite sum of Qseries. Those Qseries have integer coefficients, and I just categorify their coefficients. Now you may think this is just a total joke or stupidity. However, those series here, in the case of alternating knots, they have to do with stability of the coefficients of the Color-Jones polynomial, which Tan, Le, and I proved that they exist, the stable coefficients of the Jones polynomial. And Lev Rozansky has taken these stable coefficients of the Jones polynomial, otherwise called tails, and categorified them for alternating knots. So Lev has already categorified some of these series for alternating knots. Not all of them, but some of them. So I think this is possible to input a T, and if you look in the physics literature of the 3D correspondence, there is a T there and all sorts of other things. There is also a Homfley variable, so on and so on. But I will not say anymore. That's it. Okay.
Any questions?
Yeah.
So you explained the mystery between the tetra, or the connection between the tetrahedron and the figure eight, just in terms of the state candle, basically.
Yes.
Is there some other, I mean, rather than just do you think of it as like a low-dimensional coincidence, or a low kind of? And I still, maybe I don't. It's still mysterious to me, maybe.
Well, first of all,
I mean, are there others?
Remember I told you that this is a topological invariant, but I also said that the input is not a knot, it is an ideal triangulation. So given an ideal triangulation, there is a formula for this state integral. So if you use 3 tetrahedra, there is a triple integral that you have to do here of 3 quantum dialogues times something. Now suppose you do a Pachner move, a 2-3 Pachner move, so you get 4 tetrahedra. So there's going to be a 4-dimensional integral of the product of 4 quantum dialogues. Okay, but this is equal to that because it's topological invariant. Yes, I know. But just because it's topological invariant, the integral is different and the integrand is different. And if I use 2 different integral representations, I'm going to get the same series. I always get the same series, but presented in different way. And the Qseries identities are a reflection of the fact that this is a topological invariant, so no matter how I calculate, I always get the same answer, but it doesn't look like the same as I showed you. So, in fact, you can even ask a question, is it really true that all Qseries identities come from Pachner moves? Well, that's kind of a question, do all identities among periods in the sense of Qseries-Zagier come from change of variables in multi-dimension? These questions are motivic cohomology questions, and they are not kind of easy questions. But is there a systematic method to generate all Q-series identities? If that were true, you can have an automatic proof of identities of Q-series identity. You will not need Ramanujan. But it's not so simple. Okay.
Any other question? Okay, let's thank the speaker. 1 minute.
Yes, I mean, we talked a little bit actually. This is a different problem we are doing now. Basic, and it's induced graph counting, and we prove that an algebra of every stable coefficient of all the Jones polynomial is given by induced graph counting, and those induced graph countings are polynomials of free polynomial algebra. The freeness is where graph theory really enters. And we have formulas. This is different from, I think we were talking about the lattice of flows and the lattice of cuts. This was in this work. Baker. And tropical theorem. Yeah. So here it's a completely, you're counting graphs, but you're only counting planar graphs, induced planar graph countings, and there is a corresponding flag algebra, Razborov, yes, sorry, and it's a free algebra, there are no relations. Freedom is great, because if there are no relations, you know that it's easy to prove that if there are no relations, the only identity is A equals A, you know? If there are relations.
First experiment was the fundamental closed surface.
Closed surface, I see.
After that I switched to the free group.
Free group, yes. Yeah. Even one relation can kill you.
Especially this non-real one.
Yeah, oh, that's nightmare. Yes. Okay.
Тогда вот эта картинка, она восстанавливается.
Да, вот еще формальности ради, вот если будет вот так. Давайте x, y, z, w.
Ну, то есть
Как написать соотношение?
перевернуться,
Мы переворачиваем
вот такая точность.
и пишем, значит, чего?
У вас же есть левый и правый. Верхний.
Левая верхняя, да, есть ТТТ и правая верхняя. Значит, нам нужно верхняя. Получается здесь z, есть tx минус 1 и правая верхняя. t минус 1 и t. Ну ладно, тогда.
Потому что это же не в пространстве, а все в этом. Нет, я-то хочу понять общую методику, как писать группы, вложенные в толщинную поверхность.
Да, вот, значит,
Может быть, оттуда все.
и я знаю, на компьютере это можно сделать. Ну, в смысле, что алгоритм есть, конечно.
Нет,
но он вручную, если его считать, это будет немножко длительно. Для трилистника еще реально вручную посчитать. Ну ладно, я вам покажу такой алгоритм.
Нет, надо все равно понимать, как это устроено. Если мы хотим доказывать, будет она изоморфна только.
Ну, ее нужно посчитать для начала, для вот этого трилистника. Что там будет?
Не, ну мы посчитали. У нас есть статья, я могу